To learn a new method or theorem, I always believe it's the best thing to do a question to practice it and to sort of visualize it better. So let's do this question to gain some intuition on the Bayes' theorem and what it does for us and what it is. So a certain disease affects 1% of the population. If a person has the disease, the test correctly returns a positive result of 99% of the time. So the test isn't always correct. And if a person does not have the disease, the test incorrectly returns a positive result of 1% of the time. So somebody could be healthy, but it may show they're diseased anyway 1% of the time. You take the test and it comes back positive. The question we're trying to answer is, what is the probability that you actually have the disease? So P of the probability of you being diseased, given that the plus being that you tested positive. So this is a conditional, and this is right up the alley for the Bayes' theorem. Burns theorem. I always get confused on how to say it. And what Bayes' theorem tells us in this case, or what it helps us to do, is to find this exact probability. It tells us that some conditional is equal to the probability of both things happening at once. So someone is diseased and test positive in this case, divided by the probability that they actually tested positive. So this is exactly what we gotta do for this question. But now how do we find each of these things? Well, let's start with the numerator. What's the probability that someone is diseased and tested positive? Well, I think a good scenario to do, and don't ego yourself into not doing it, is just drawing it out with a tree diagram, right? So given some person, there's a 1% chance that they are diseased, and a 99% chance, correct, that they are just healthy. Okay, they're fine. But now out of these things, remember that there was a false correct rate and a false positive rate. So given our diseased people 99% of the time, and we're doing these in decimal, this isn't 0.01%, okay, this is 1%, and this is 99, that they do test positive, and there's a 1% chance that they actually test negative. And out of the healthy people, there's a 1% chance that they test positive, and a 99% chance that they test negative. And so for in our case, we're trying to find the probability that they are diseased and test positive. So we find the cases where they're diseased and test positive. Okay? So in this case, diseased, and test positive. So the probability is our 0.01 of actually being diseased in the first place, and our correct positive test result of 99%. So that is, let's say, the first thing we gotta do. Now, secondly, we're gonna find the probability that they actually test positive. which in our case is here and here. Using the sum rule, we can just sum up when they're positive here with the cases that they're positive here, or the probabilities that they are. So we can reuse what we got here. So 0.01 times our 99% summed up with the other case where they test positive. So 99% case they're healthy and 1% chance they test positive. And it gives us this. And if we put these two things together according to Bayes' theorem, we get the probability that they are actually diseased given that they test positive. So given that they test positive, right? That's what a conditional is. Given positive, so we're already assuming that this is true. Then we got here 0.01 times 99, 0.01 times 99 summed up with the sum rule. And the sum rule works because, we're doing one or the other. Either can be true. And this gives us 0.5. So a little unexpected, quite high, but that makes sense though. So it's saying that 50% of the time, if you test positive, it means so only 50% of the time, you're actually diseased whenever you test positive. And so given the question saying you take the test and it comes back positive, your odds are half that you're even diseased. So the probability is 50%. And now to explain a little more about what Bayes' theorem does for us, except for this like dinky formula that you keep seeing and maybe you learn about once or twice, but it's best to get some intuition. So when you think Bayes' theorem, think updating beliefs based on new data, right? So given our case, right, where we had somebody and they were diseased or they could be healthy, originally, if you were asked the probability of they are actually diseased, well, it's 100%, right? Only 1%, like, there's no false positive, there's no whatever, it's 100%. And there's a 100% chance that you test negative. But given this new information that there is a false positive and false negative, so let's say new data, original, and so I shouldn't have erased it, but let's say 99.1.1. This is 99. So given our new data that there is a false positive, false negative rate, our probability then becomes, given that they're positive, is 50%. Originally, we would say 100% of the time. So given new data, we update our beliefs about the probability using the Bayes' theorem. That's what it's all about. And here we're of course supposing I think a very important fact to mention is that the positive or negative rate could be anything. It could be A and B, and you know, given A and B are events, and the probability of B is above 0, then this holds, and it's a neat trick to learn. And the reason why this has to be above 0 is, of course, in our formula we put the probability of B here, and if it's 0, then you can't evaluate it. And a couple other formulas I want to mention is that it's not only given that they're positive, or given B that A is true in this case. You can also rewrite this as well. The probability of A and B is equal to the probability of B times A given B. Right? That's exactly what we have here. We're just multiplying each side by the probability of B. Another fact that we can derive is that, or not really derive in this case, but another fact that is true that the Bayes' theorem tells us is that the probability of some event A given B is also equal to the probability of B given A times probability of A divided by probability of B. And so again, it's all about using information or new data you already have to update previous existing probabilities that you know. And just another way of visualizing this again is, instead of a tree diagram, let's use a Venn diagram, right? So little circles. Okay. Given our example, let's say that this is the group that actually tests positive, and this is the group that is actually diseased. Well, this overlap in the middle here is the probability that they're diseased and actually test positive, right? And so we're really just finding this overlap. So the probability of being diseased, given that, is the overlap between the two sets divided by the whole circle, or the whole plus the circle, which is our probability of B. Our probability that they are actually, or that they test positive.